Hello everyone, I am Abdullah Mamun from Development of Computer Science Engineering BRAC University. Today I'll talk about UNIT, a deep learning model that has revolutionized image segmentation, a critical task in fields like healthcare, agriculture, and autonomous driving. Traditional image segmentation struggled with precision and scalability, but deep learning provided a solution. Among various models, UNIT stands out as a game changer, offering pixel level segmentation with remarkable accuracy. So let's dive into UNIT, a groundbreaking convolutional neural network designed specifically for image segmentation. UNIT was introduced by Olaf Ronneberger in 2015, initially targeting biomedical applications. What sets it apart is its ability to combine precise localization with pixel-wise classification, making it exceptionally powerful for detailed segmentation tasks. Its unique architecture has made it indispensable not only in medicine but also in fields like remote sensing and autonomous driving. The model is a testament to how deep learning can revolutionize image analysis. UNET, introduced in 2015, revolutionized image segmentation, gaining traction in medical imaging by 2016. Variants emerged in 2017, expanding its scope beyond biomedical applications by 2019. Recent years have seen advancements in training techniques and transformer integration, making UNET a cornerstone of modern segmentation tasks. Okay, now let's dive into the UNIT architecture. It consists of three main components: encoder, bottleneck, decoder. There is skip connections as well. The encoder extracts features from the input image while progressively reducing its spatial dimensions. Each step involves convolution layers, relativations, and max pooling, capturing patterns at various scales. Bottleneck at the architecture center is the bottleneck, which represents the most abstract, high-level features. It acts as the transition point between the encoder and the decoder. The decoder reconstructs the spatial dimensions of the output. It upsamples the feature maps using transpose convolutions and refines them with the help of feature paths through skip connections from the encoder. Skip connections ensures that spatial information isn't lost during downsampling, making units so effective at tasks like biomedical segmentation. So let's dive into unit architecture a little bit more. So let's explore the core components. The encoder, the first hub, begins with a series of train to tree convolution layers, each followed by a relay activation. This tracks initial features, then a 2 into 2 max pooling operation with a stride of 2 downsamples the features, effectively halving the spatial dimensions while doubling the number of channels to compensate for the loss of spatial information. This process of convolution, relativation, and max pooling repeats at each stage, progressively reducing spatial resolution and increasing feature complexity. Now consider the decoder. It just mirrors the encoder. Here 3 into 2 convolution layer followed by relativations are employed as well, but instead of downsampling, we upsample here. A 2 into 2 convolution layer halves the number of channels. This upsampling restores spatial resolution lost during the encoding phase. Crucially, the encoder and decoder are interconnected to two types of paths: connecting paths and a bottleneck. Connecting paths simply copy features from symmetrical encoder stages and concatenate them with the corresponding decoder stages feature. This feature leverages both the semantic information from the decoder and spatial detail from the encoder for precise segmentation. Suppose from the decoder we got this is a bike. So in the from the encoder, then this would be the bike's pixels. So it would be the precise segmentation. The bottleneck acts as a bridge between encoder and decoder. The features are downsampled, passed through convolution layers, and then upsampled to the pre-bottleneck resolution before entering the decoder. In essence, the input image passes through the encoder, undergoing successive convolutions, value activations, and downsampling. The bottleneck processes these features. Then the decoder upsamples, concatenates features from the connecting paths, and continues through convolution layers and relay activations until a final output layer produces the segmented image. This symmetrical interconnected structure makes UNIT exponentially effective for complex segmentation tasks. So now let's talk about the activation function used in UNIT. Our value or rectified linear unit is an activation function defined as f of x equal max of 0, x, meaning it outputs the input if is positive and 0 otherwise. Its widespread use stems from simplicity, computational efficiency, and ability to mitigate the vanishing gradient problem, a common hurdle in training deep networks. In UNIT, value is instrumental in both the encoder and decoder pathways. But focusing on positive activations, often the most relevant features really facilitates effective features extraction and refinement. This selective activation contributes to the model's overall efficiency and stability during training, making it ideally suited for units demanding image segmentation tasks. So if you look at the graph in the picture in our presentation slides, we'll see when the graph is plotted, we can see the max we're gonna get is x, and the minimum value is 0. So if the input is positive, we're gonna get that. Otherwise, the value would be 0. Okay, let's walk through the journey of an image in unit. First, the encoder acts as a feature extractor. It uses convolution layers to analyze the image, extracting increasingly complex features. Each layer is followed by relay activation to sharpen those features and max pulling downsample the image, focusing on the most crucial information. This continues until we reach the bottleneck where the most abstract features are represented. Next, the decoder takes over, upsampling the image to restore its resolution. At each step, it receives guidance from the encoder through skip connections, combining high-level features with low-level details for more accurate reconstruction. The bottleneck's role is crucial. It refines the features before sending them to the decoder, ensuring high-quality output. Finally, the decoder produces the segmentation map, where each pixel is accurately classified, completing units, detail, and precise segmentation process. UNIT's remarkable success in biodynamical image segmentation shouldn't overshadow its limitations. Its sophisticated architecture, incorporating numerous layers and skip connections, demands significant computational resources, making it potentially unsuitable for resource-constrained environments. Furthermore, the risk of overfitting is a real concern, particularly when training with limited or imbalanced datasets. While techniques like data augmentation can mitigate this, it remains a crucial consideration. Another key limitation is UNIT's relatively limited ability to grasp global context. While it excels at capturing fine-grained local details, it may struggle to integrate broader spatial relationships with an image, potentially affecting the accuracy of larger scale segmentations. Finally, the model's performance is highly sensitive to noise and inaccuracies in the input data or its labels. Addressing these challenges, the computational cost, overfitting susceptibility, global context understanding, and robustness to noise represents fertile ground for ongoing research and improvements of unit and similar architecture. Unit's versatility is truly remarkable, impacting diverse fields with its powerful image segmentation capabilities. In healthcare, imagine its role in identifying cancerous tumors in medical scans with unprecedented accuracy, aiding in earlier and more effective treatment. Or consider its use in segmenting organs for surgical planning, providing surgeons with detailed 3D models to improve precision and minimize invasiveness. Beyond healthcare, UNA's applications are equally impressive. In satellite imagery analysis, it can accurately classify different land cover types from forests and urban areas to agricultural land, enabling efficient monitoring of deforestation or changes in urban sprawl. This data is vital for environmental conservation and urban planning efforts. For example, it can help track the spread of a desert, allowing for proactive interventions. Autonomous driving heavily relies on UNET's real-time object segmentation to ensure safe navigation. It identifies pedestrian vehicles and lane markings, providing crucial information for self-driving systems. In agriculture, UNET can analyze images of crops to detect diseases at early stages, allowing farmers to intervene promptly and prevent widespread crop damage, leading to improved yields and reduced pesticide use. Finally, in art restoration, UNIT can meticulously analyze damaged artwork, helping conservators to digitally reconstruct missing parts or enhance faded details. These diverse applications highlight UNIT's transformative potential across different sections. In conclusion, UNIT has proven to be a powerful and efficient tool for image segmentation. Its unique architecture, combining an encoder for feature extraction, a bottleneck for feature refinement, and decoder for high resolution reconstruction, allows it to deliver precise pixel-wise segmentations. With the addition of skip connections, UNIT ensures that both high-level semantic and low-level spatial details are preserved throughout the process. This has made it an essential model not only in biomedical applications but also in fields ranging from remote sensing to autonomous vehicles. UNIT's flexibility and accuracy truly make it to go-to solution for challenging segmentation tasks. This has been my presentation. Thank you so much for listening.